College Algebra. Welcome to, I think this is your first video that I've made for you guys. I don't know exactly where I am right now as you watch this, but I don't know. I hope you learned something from it, a little different. So this is a really important topic. We've talked about logs for a few days now, and now we're going to get into a little bit more of the properties of logarithms. It may seem like magic. I hope we can dispel some of the magic and make some sense of this. So, with no further ado, that's not what I want to do. Let's go into here. We'll go up into full screen. So we're going to quickly look at the properties of logs. Okay, so first we'll do a quick review. An exponential statement or equation could look like this. We could write something pretty easy like 2 to the third power equals 8. Now it's very important, this is not 2 times 3. This is 2 to the third power, 2 cubed. 2 times 2 times 2. You multiply it 3 times. 2 cubed equals 8. All right, and the log equation that goes along with that, right, what would that be? A log is always a question. This is the base, so it's the log, the base is 2 of 8 equals 3, right? Log base 2 of 8 equals 3. So, what exponent do I need above a 2 to get an 8? What exponent do I need above a 2 to get an 8? That exponent would be 3. All right. So, keeping that in mind, the fundamentals. I've got to rearrange a little bit here. My arm is falling off the table. Let's write one of the first ones. Number 1. Roman numeral 1. That's important stuff. So I know, for instance, the log base 2 of 2 equals 1, right? Why is that? Because 2 to the first power gives me 2. What exponent do I need above a 2 to get a 2? Well, 2 to the first power, right? More generally speaking, we'll write this as the log base b of b equals 1, right? To get any number, right, I just raise the base to the first power, and that number stays the same. Okay, so this is going to be a concrete example, and this is more generically in mathematical terms. Property number 2, I'll call this. That is the log base 2 of 1 equals 0. I should put parentheses around here. The log base 2 of 1 equals 0. Why is that? What exponent do I need above a 2 to get a 1? Well, 2 to the 0 power is 1. In fact, I can be more general about this one too. The log base b of 1 equals 0. Now, how could that be? Anything raised to the 0 power is always going to be 1. What exponent do I need above 17 to get 1? What exponent do I need above 38 to get 1? What exponent do I need above 10, above e? Anything to the 0 power gives me 1. So that's the second very generic property. All right. The third important property to know is this one is a little confusing. The log base 2 of 5 squared. Oh, no, that's not what I did. I did the log base 2 of 2 to the 5th equals, well, what is this going to equal? Log base 2. What exponent do I need above a 2 to get 2 to the 5th? Well, if I'm trying to get 2 to the 5th, I need a 5, right? What exponent do I need above a 2 to get 2 raised to the 5 power? Well, that's 5. Okay. More generically, I can write this. The log base b of b to the x is always going to be, what is it? What power do I need above a b to get b to the x? Well, that's always going to be x. So this is a good way to get at, right? To get at a variable that's up in an exponent. I can take the log of that, right? To get at the exponent, this kind of leads to the fact that exponentiation and logarithms are inverse functions. The log base b of b to the x, right? Exponent, logarithm, they undo each other, so this becomes just an x, all right? This one confuses a lot of people. Remember, when we need to undo multiplication, we do division. When we need to undo subtraction, we do subtraction. The inverse operation is addition, right? Exponentials, right? Putting a variable up in the exponent. The inverse operation is a logarithm, so they undo each other. And again, I'm forgetting my parentheses. I'll get better about that. Property 4. This is one of the trickiest ones. It's very related to 3, but for instance, 2 to the log base 2 of 8 equals, well, what will this be? All right. The log base 2 of 8, let's just look at the exponent here. The log base 2 of 8 means what exponent do I need above a 2 to get an 8? What exponent do I need above a 2 to get an 8? Well, hopefully most of us know that this is 3. In fact, I wrote it up here. Log base 2 of 8 is 3. But what do I do with this 3? I put it right back up above a 2. Right? So this is really 2 cubed. Well, that whole thing is going to equal 8. Right? And again, the more generic way to write that is b to the log base b of x is going to equal, what exponent do I need above a b to get an x? Well, I don't know. I don't know what b is. I don't know what x is. But what am I going to do with that exponent? I'm going to put it above a b, right? So of course it's got to give me an x. Now, how is number 4 related to number 3? Here I've got, I'm going to do over here. Here I've got a variable. It's, my variable stuck up in this exponent. Say I know what b is, but I'm trying to get at x, right? I've got b to the x. I can take the log of that, and that allows me to get at this exponent. That equals x. The flip side of that is, say I've got a variable that's stuck in a logarithm, right? Here's a log base b of x, here it is. How do I get rid of that? I put it up above a b, right? That's the kind of the reverse, and we'll use this tool a lot more in the next section, but here we're just trying to show you what it is. What exponent do I need above a b to get x? And then I take that very same exponent and I put it above a b. So of course that should be x. All right. Let's look at a couple examples of these. We'll write them over here. Example. Let's say I've got the log base 4 of x. Log base 4 of x equals 2. Let's say I want to know what is x. All right. Well, I've got two options. Option 1, and this is really my preferred option, is to rewrite in exponential form. Okay. Well, what exponent do I need above a 4 to get x? And that equals 2. So the exponent I need above a 4 to get an x is 2, which must mean that 4 to the second power must equal x. Okay, well, that tells me that x squared must equal, oops, nope, not x squared. X equals 16. All right, that's easy enough. Option 2, not quite as obvious, but perhaps even a little more powerful, is to use the log properties. Right? Here, my variable is stuck inside my logarithm. The variable's in the logarithm. Now, if I had, let's do a sidebar. A sidebar in green. We'll do something happy. Okay. Let's say I had 5x equals 30. Right? 5x equals 30. Well, this is multiplied. How do I do, how do I undo multiplication? How do I is that a word? Undo multiplication? right? I divide. So we'll divide each side by, divide this side by 5, divide this side by 5, then I get x equals 6. Okay? Because my x was bound up with this 5 by multiplication, so I used division to undo that. All right, now if I go over here to this problem, my x is stuck in my logarithm. Well, what property undoes logarithms? Exponentiation and logarithms are inverse operations. They undo each other. So I can say 4 to the log base 4 of x equals 4 squared, right? Now, how does that work? Well, if the log base 4 of x is the same as 2, if the log base 4 of x is the same as 2, up here, log base 4 of x is the same as 2, well then 4 to the log base 4 of x has to be the same as 4 to the 2 power, right? These have got to be the same. I just put them both above a 4. It's got to be the same. Now, what exponent do I need above a 4 to get an x? I don't know, right? But where am I going to put that exponent? Above a 4. That's this property over here. I'm exponentiating this thing. So this thing just becomes an x, and this is 4 squared. So x equals 16. Right? Same answer both ways. This is much more direct, right? We just rewrite in exponential form, knowing what the logarithm really is. This is using a property. In fact, this is using the fact that exponentiation, putting this up in the exponent, and taking the logarithm are inverse operations. Important to note, though, this is important that my base that I use here is the same as down here. Right? That's what allows me to do that. All right. So let's do another example like that. Next page. Back to black ink. Good. Let's say I have a little more complicated equation. Let's say 2 times the log of 7x plus 1 equals 4. All right. Well, this is an equation. Sure, it's got a logarithm in it, but it's still just an equation, and we do the same old stuff. The easiest thing to get at is this plus 1. This is the last thing we would do, order of operation wise, so it's the first thing we undo. What am I going to do here? I'm going to subtract 1 from both sides. Minus 1, minus 1, and so that gives me 2 log of 7x equals 3, right? No problem so far. I'm not exactly sure what's going to happen here, but I'm not worried about it, right? I'm just going to do my other stuff. Well, this is multiplied here. This is multiplication. So I can divide this side by 2. Whoops. Let's get rid of that. Let's do that in blue so you know what I'm doing here. Sorry guys, I'm a lot of practice. 2 log of 7x. We'll do this in blue. We're going to divide both sides by 2 to get rid of that 2. Divide that by 2. And so what do I have now? I've got simply the log of 7x equals 3/2. So we're going to leave that as a fraction. Now, we remember that when I write log and I don't indicate any other base there, when I don't give any other base, we assume that the base is 10. All right, so I'm going to put a little 10 in there. There's a log base 10 of 7x. What exponent do I need over 10 to get 7x? Well, that exponent is 3/2. All right. First option is to use the exponentiation property. How do I undo a logarithm? My variable is stuck inside this log. I put that in an exponent. So I'm going to say 10 to the power log base 10 of 7x equals 10 to the power 3/2. Right? So this is a logarithm. How do I undo the logarithm? I exponentiate it. right? 10 to the log base 10 of 7x. What exponent do I need above a 10 to get a 7x? Now I have no idea. But where am I going to put it? Above a 10, right? So what am I left with? I'm left with a 7x equals 10 to the 3 halves. What does that mean? I'm going to write this as 10 cubed to the 1/2 power, right? We talked about that when we talked about exponents. And so I could divide this both sides by 7, right? How do I undo multiplication? I use division, right? The inverse operation. And so finally I'm left with x equals, well, this is pretty ugly to look at. So 1/2 power is really a square root. 10 cubed is really 1,000, so this is the square root of 1,000 over 7. Right? So there's my answer. All right. Now, alternatively, an alternate path, maybe a little more direct, maybe a little easier, is down here. Right? I know that the log base 10 of 7x equals 3 halves. What does that mean? The exponent above a 10 to get 7x equals 3 halves. So my base is 10, my exponent is 3 halves, and that equals 7x. So x equals 10 to the 3 halves over 7. Right? So, and then I can rewrite that as the same thing, right? It's the square root of 1,000 over 7. Works out both ways, about the same number of steps. Some of you might find this a little more intuitive, or at least less confusing, that an exponent undoes a log. Some of you might feel more comfortable just rewriting a log expression as an exponential expression. All right? Either way it works. Think about which way makes more sense to you, and then let me know. So that's it. Let's. I'm going to skip a page here, and so whenever you have a booklet and there's a blank page, it always says notes. So call that notes. Next page. More log properties. More log properties. All right. The first one, and probably the one that comes up the most, I would say, is if I have, let's call this the multiplication. I'll write this. The log of two numbers multiplied together, m times n, equals, now what's that going to be? So since I don't have a base here, we'll just assume that base is 10, right? That's how we do it. So this is some power of 10, right? I don't know, it's going to take some exponent, right, to get to 10 to some power will give me m, just like 10 to some power will give me n. 10 to some power can give me m, 10 to, so if I multiply these two, 10 to some power and then 10 to some other power, what do I do with those exponents? I add them, right? I would add the exponents if I multiply these two things. So if I can add the exponents of these things, I'll just add the exponents of these things, right? Log of m plus the log of n. Now that may not make sense. All right, so let me do a little example of this one. Let's say I want the log base 2 of, let's see, 16 is 128. All right, how is that going to work out? I could certainly write this as the log base 2 of 8 times 16, right? Which is the same as the log base 2 of 2 cubed times 2 to the 4th, right? So here's 2 powers of 2 2 powers of 2. And that equals, let's see, what power of 2 would it take? Oh, so this 2 to the third times 2 to the fourth, that equals log base 2 of 2 to the seventh equals, right, log base, what exponent do I need above a 2 to get 2 to the seventh? That equals 7, right? Alternatively, I could have split this up into the log base 2 of 2 cubed plus log base 2 of 2 to the 4th. Right? If I'm going to multiply the numbers, I add their exponents. Right? And so since the logarithm is the exponent, I can just add those exponents separately. Because this is equals 3 plus 4, which is 7. So it's the same thing, right? It kind of goes in circles, but it is all the same thing, right? All this stuff is all different ways to write the same thing. All right. Now, similar. Oh, I should make an important note here. Let's do this. A lot of people will do this. Log base whatever of m times n, and you'll write that as the log of m times the log of n. Okay, that is not true. That's a huge mistake. Do not write this. That's not true. Okay? The log base m times n, you can't just split it up and multiply those two things there. Right? That doesn't work. A very similar property to this is division. All right, if we do a division property, and I'll see if you guys can guess what this is. The log of m divided by n equals, what do you think? If I'm dividing two numbers, what do I do with their exponents? Right? I would subtract their exponents. Right? So this becomes the log of m minus the log of n. Right? Now, another common mistake is the log of m minus n equals the log of m minus the log of n, right? Again, that is wrong. Do not do that. The order of operations says I have to do the m minus n first. I can't distribute a log. This is not multiplication. This is not log times m minus n. This is the logarithm of. This is a function. It's a special function. Right? We cannot distribute a log. It's not multiplication. But we can use this property that since we subtract exponents, we can subtract exponents. All right. And the third property that I think is pretty cool is the power. Right? So let's say if I have the log of m to some power, right? If I raise it to the p power, well, what is that really? That's actually log of m times m times m times m, however many times I have to do that, right? And then so I can add all those up, equals the log of m plus the log of m plus the log of m plus dot dot dot, p times. Well, so what does that equal? If I add them up, p times, it's p times the log of m. Right. Let's look at a little more concrete example of that one. Let's say I want to do the log base whatever of m cubed, right? That equals, well, we know it equals 3 log of m, right? What can I do? I can just pull that power out front, right? So this equals p times log of m. Right? I pulled my exponent out front, p times the log of m. It's really just an extension of this multiplication property. But if I do it an actual 3 times, this equals log of m times m times m, which equals the log of m plus the log of m plus the log of m, right, which equals 3 times the log of m. Okay, so I can do that with any exponent, right? Especially when there's a variable up here in the exponent. Taking the log of both sides is a great way to get the exponent out front, all right, to get at that exponent. All right, why is that? Because logs and exponents undo each other. All right, so what is the true value, right? What is the value of logs as a tool, right? Why is this useful to me? Because one of the, and I tell you guys this all the time, oh, I gotta pause it and turn the heat off. Hold on for a second, the heat came on, it's gonna be too loud. Okay, so what's the value of this? Remember that one of the big goals in mathematics is to rewrite a problem to make it look like we know how to do. All right, so let's rewrite some expressions and we're going to condense them. Okay, and what do I mean by condense? I mean something like this. Say I have log base 2 of 6 plus the log base 2. Log base 2 of 7. How does that work out? Well, I know from my previous properties here that when I multiply the numbers, I add their exponents. Alternatively, when I add the exponents, I can multiply the numbers. When I add the exponents, right, the log is an exponent, log is an exponent, I can multiply the numbers. I can do that over here. So log base 2 of 6 plus the log base 2 of 7 is the log base 2 of what? Of 42. Right? 6 is 2 to some power. I don't know what that is. 2 to some power. Right? And this is 2 to some power. Right? That's the same as the, and if I'm going to add these two exponents, it's going to be 2 to some bigger power, the power added, which really means I had to multiply these things together. So it's the log base 2 of 42. All right, let's do another one, similar. Let's say the natural log. That's one example. Here's another example. The natural log is the natural log, which is really the log base e. Let's say there's a variable in there, x minus 5, right? Minus the natural log of x, right? How can I rewrite this? Well, if I'm subtracting the exponents, that must mean I divided the numbers. So this is the natural log of x minus 5 over x. Right? That's the subtraction property. If I'm subtracting two exponents, that means the other way to do it is by dividing the two numbers. All right? Good. What about one that's a little more complicated? Let's do let's make a bigger one here. How about 2 times the log of x minus 1/2 the log of x squared plus 1. Right? Boy, a lot of stuff going on here. I got addition, subtraction, I got some multiplying here. Well, I know that one of my properties, my power property, allows me to move the p out front, or if I have a p out front, I can put it up. If I have a p out front, I can put it up here, or if I have an exponent up here, I can put it out front. Right? Either one, they're the same thing. So if I'm trying to condense these two things together, I'm going to rewrite this one as the log of x squared minus the log of x squared plus 1 to the 1/2 power. Okay. Well, the log of x squared, I'm going to leave that as the log of x squared. But what can I do with this? The 1/2 power, that's really like the same as writing the square root of x squared plus 1. And when I subtract exponents, that's the same as dividing. Log of x squared divided by square root of x squared plus 1. Right? Okay, good. Now it works the other way too. We can rewrite and expand. Right, this is kind of nice. Say if we're trying to solve an equation and we want everything in one term, right? We can start with this whole thing and then just condense it down into one log, but a much more complicated expression. But it's a single log. Let's say we want to go the other way. Let's say I have the log of x cubed times x plus 1. I guess that'd be easy enough to distribute, but we'll leave it like that. X plus 3 squared. And let's square the whole thing. Okay. Wow. So we have a really complicated expression here. The argument of our logarithm is very complicated. What if I wanted to make just a bunch of simple logarithmic statements? Let's try that. First of all, this little power out here can come out front. So that we'll write this as 2 times the log of this whole thing. X cubed, x plus 1 over x plus 3 quantity squared. All right. Well, here I'm dividing two numbers, right? Another way to divide two numbers is to subtract their exponents. So I can write this as 2 times the log of the top, which is x cubed times x plus 1, minus, I better put this in here, the log of x plus 3 squared. Why are these brackets important here? I forgot to add those when I first did it. Because it's 2 times all of this. And let's do that in a blue box. All of this, oops, all of this is all of this. Right, that's the same thing. So I have to do 2 times all of that, so it's really important that I distribute that 2 back in there. Okay, well, let's keep going. So here I'm multiplying two things. That's the same as adding the exponents. 2 times the log of x cubed plus the log of x plus 1. minus, oh, here's a power, that can come out front, 2 times the log of x plus 3. Alright, and finally here's one more power. I can move that out front, so it's 2 times, wow, this is getting huge, 3 log of x plus the log x plus 1 minus 2 times the log of x plus 3. And I guess I could distribute this through, then makes the whole problem, a bunch of simpler things. This would become 6 log x plus 3, oh, that's it, 2 is a 2. Now the heat's coming on again. 2 log x plus 1 minus 4 log x plus 3. Alright, so what did I do here? Let's make a little note. Over on this side, I took several simple logs, or 2 simple logs, and I made 1, right, hard log. And over here I took 1 hard log, right, and maybe I would prefer that would be 1, 2, 3 simple logs. All right. And we'll get a much better feel for this. We'll get to apply these tools in the next section. And actually solving a bunch more equations using these very convenient properties of logarithms. That's it. I hope you learned a little something. The homework is up on Alex. Give it a shot, and we'll see you soon. I want to get that to full screen. There we go. Catch you later.